Welcome to Chapter 10, Lesson 3, where we're going to be discussing inference for linear regression. So this is going to be the last type of inference testing that you are using in AP Statistics. Go ahead, take a minute, read what we're going to be doing in this section, and then we'll go ahead and get started. All right, so let's just take a look at what exactly a inference for regression is going to look like. So when a scatter plot shows a linear relationship between a quantitative explanatory variable and a quantitative response variable, we in the previous lesson used the least squares regression line fitted to the data to predict y for any given value of x. So here's what we're going to take a look at. If the data was from a random sample from a larger population, we are actually going to need statistical inference, which is our inference testing, to answer questions like this. Is there really a linear relationship between x and y in the population, or could the pattern that we see in the scatter plot happen just by chance alone? It just so happened that those points that we picked happened to form a line in that particular sample. In the population, how much will the predicted y value change for each increase in the 1 unit in x? So what does that look like? That's the slope. So basically we're checking to see, all right, how much is the predicted value of y going to change for every increase of 1 in x? Now, the next question is a little bit trickier. What is the margin of error for this estimate? So basically, what is the error going to be when I predict the y value for every one change in x? So kind of what's the margin of error for our slope, basically. Does any of this sound familiar? Does this sound like statistical tests like we've done in the past? If you take a look at the first one, this is a test of significance. The second one, if we're estimating the margin of error or how far off we are from the slope, that's talking about our confidence interval. Let's take a look at the scatter plot below. It goes over the duration and interval of time until the next eruption of Old Faithful. So this is the duration, okay, in minutes, and this is the time of the eruption for the Old Faithful geyser for all 222 recorded eruptions in a single month, okay? Now let's take a look at the least squares regression line. The least squares regression line for this population data has been added to the graph. Now, this is actually the population regression line, or the true regression line, because we are using all of the observations, the entire population, for 1 month. So the predicted interval of the eruption is 33.97 plus 10.36 times the duration. Now I want you to notice it says predicted interval. So since it says predicted interval, that's why they don't have the hat on top of it, because they said the word predicted. Now, let's say that we take a simple random sample of 20 eruptions. So let's say we take 20 of these eruptions from this population and calculate the least squares regression line for the sample data. So this is all 222. Let's just pick 20 of them. What is that going to look like? How is the slope of that sample of 20 going to relate to this slope right here that's going to be the slope of the population for all 222? Are they going to be the same? Are they going to be different? Are they off by a little bit? Let's take a look at what that looks like. So the figures below show the results of taking different simple random samples of 20 Old Faithful eruptions this month. So if you'll notice here, these are 20 eruptions from all 222. We drew the line and calculated the least squares regression line. Let's take a look at the slope. The slope of this one is going to be 10.2. Here's my second example. So this is 20 different samples. Notice my line looks a little bit different because they're different samples. My slope in this case is 7.7. This one I took 20 different samples, drew my least squares regression line, and this slope is a positive 9.5. Okay, now each graph displayed the different samples that we took, and it produced different lines, different slopes, and different y-intercepts. Take a look at how those all compare to the population regression line that we took when we had all 222 samples. Now, the population slope was 10.36. Let's compare that to the slope of the sample. The slope of the sample was 10.2. 7.7, and 9.5. Now, obviously, the samples are not going to be the exact same as the population because remember, our samples are used as an estimate. In this case, we're using our sample slopes to estimate the population slope. Now, we're going to take a look and see, well, how far is that slope that we got from the sample off from the population slope? Remember, confidence intervals and significance tests about the slope of the population regression line are based on the sampling distribution of the slope. So what exactly does that mean? Okay, so we're going to take a look at the sampling distribution of the slope. So if you notice here, we did sampling distributions before. When this says n equals 20, this right here is the slope from 20 of those 222. This right here is the slope from 20 of those 222. That's what each of these represent. Each of these we took a sample of 20, and it is the slope of that 20, okay, the regression line that was created from those 20 specific values that we took. All right. So let's see what exactly the sampling distribution of B is. The graph at the left is 1,000 different slopes. So basically, we did 1,000 samples of size 20. So this is size 20, this is size 20, this is size 20, this is size 20. They're all size 20. We did that 1,000 times. Each of those 1,000 times, we calculated the slope. So these are all little slopes in here, okay, from your samples of size 20. Then we put all of those slopes on the graph to see what the sampling distribution would look like. Does it look familiar? Does it look like a normal curve? Hopefully it does. Okay, now let's describe what the sampling distribution of the slope looks like. Do you remember SOX? Hopefully you do. So let's take a look at the shape. The shape here, we can see that the distribution of the slope is roughly symmetric and unimodal. Now remember, roughly symmetric and unimodal is what says that is going to be normally distributed, okay? You could also use a normal probability plot to verify that it's normal, but it's symmetric and unimodal, therefore it's normal. What is the center? So the center, the average of all of these 1,000 B values, so you have 1,000 B values in here, what should it be the same as? It should be the same as the population slope of 10.36. If the population is 10.36 and I average all of my samples, then the average of all your sample slope should also be 10.36 or close to that. Now let's take a look at the spread. The standard deviation of the values is 1.29. Now later we'll see that the standard deviation of the sampling distribution is 1.27. But just so you kind of see what that looks like, and that would be given to you, you would not need to calculate that right now. All right, let's take a look at this example. The population regression line for Old Faithful is given below. Notice how I have the hat on top of interval, okay? The A value right here, the 33.97, that is actually the y-intercept for the population because this is the population regression line. The B, this is the slope for the population because this is the population regression line. Remember our standard deviation of our residuals? Sigma is actually representing the standard deviation of the residuals here is 6.131. Now remember what that means. That means on average, we're going to be 6.131 amount of interval time off from the predicted value. And remember your standard deviation of the residuals is always in terms of y, since we discuss, since the residuals is your vertical distance or your distance in y. Now, if we were to take all possible samples of size 20 from the population, we would get the actual sampling distribution of B. What should the center, shape, and spread of that sampling distribution look like? Remember, if a statistic is an unbiased estimator, then the mean of the sampling distribution is equal to the mean of the parameter. So what does that mean in this case? Number one, we should get something that's approximately normal. Number two, the mean of the center here is actually going to be the slope of the population regression line. So notice the mean of our sampling distribution is the same as the population slope. Okay, so instead of using mu's here, we're actually going to end up using this big beta, which means your slope in this case. Now let's look and see how we are going to find the standard deviation. The standard deviation here is sigma, which is your standard deviation of your residuals, which was given to us above here, all over the standard deviation of x times the square root of n. This information will be given to you. Standard deviation of x, your sample size. The spread, is 1.27. So that's your standard deviation of the slope. Well, what exactly does that tell us? That tells us, on average, how far away our sample slope is from the population slope. All right, now let's take a look at the formal definition of a sampling distribution of a slope. Number one, when you choose a simple random sample of n observations of x, y from a population of size n with a least squares regression line, the population regression line is your predicted y equals alpha, which is your y-intercept, plus beta. Notice this is a big B, so this tells you this is your population slope, big beta, okay? Let b, little b, is going to be the slope of the sample regression line. So make sure you understand the difference between big B, population slope, little b, sample slope. The population still needs to be 10 times the sample size. That's your 10% condition, okay? The mean of the sampling distribution, so we said when we draw that sampling distribution, this is all slopes. The average of your slopes is going to be the same as your population slope. The standard deviation of the sampling distribution is as follows. So standard deviation of your slope. Now notice this is the slope of your sample. Okay, this is not the population because we have a little b here. This on top right here is your standard deviation of your residuals. This down here is going to be your standard deviation of your x values times the square root of your sample size. Okay, now we just talked about what those 3 points were in that formula. So remember, this is your standard deviation of the residuals. Since it's in the numerator, okay, when your standard deviation of your residuals is larger, that's going to mean that your standard deviation of your sample slope is also going to be larger. So think about it this way. If the points are more spread out over the true regression line, then there's going to be more variability in the slopes. So what do I mean by more spread out? I'm talking about if there's points above and below the line, and here's your sample regression line. If the points are more spread out like they are over here, then there's going to be more variabilities in the slope. Let's say I pick these points right here. Here's what my slope would look like, my sample slope. Next time I pick these points, this is what it looks like. So the slope is actually varying a lot when you go from take different samples of different sizes. And just remember, here your standard deviation of the residuals tells us how far away on average the observed values are from the predicted values. Now this number down here is your standard deviation of the explanatory variables. Since it's in the denominator, if you have a large standard deviation here, then your standard deviation of your slope is going to be smaller. More variability in the explanatory variables. That means I have a lot of variability. I have many different samples in my explanatory variables, leads to a more precise estimate of the slope. Think about it this way, having the points more spread out across the x-axis rather than being all bunched together. So basically what that means is if I'm going to have points kind of all over about the x-axis versus having them a whole bunch of x values clustered right here. So it's going to give us a better estimate if your x values are more spread out. Now, n is my sample size. As the sample size increases, the variability decreases, and once again, we'll have a more precise estimate of the slope. Sound familiar? Same thing you did in your previous units, okay? Let's just take a quick minute and talk about the normal condition. The sampling distribution of B will be approximately normal if the values of the response variable y follow a normal distribution for each of the explanatory variables. So basically what that means, it's going to be approximately normal if I take all of the slopes, put them in a sampling distribution, and they look approximately normal. So the sampling distribution is if I take many samples of size 20 or whatever, and I find their slopes, and then I put them in a graph to see what they look like. And make sure you're stating that it's unimodal and symmetric, therefore approximately normal.